for part 1. This is the first lecture for the lecture 4. And so the first topic we'll be talking about is atomic spectroscopy and the Bohr model. Specifically, we'll be focusing on atomic spectra right now. So atomic spectra is when an atom absorbs energy in the form of heat, light, electricity, or any other form of energy, and re-emits this energy as light. So for example, this is what happens in neon signs, and different atoms will emit different colors, which explains why neon signs will also have many different colors. So if you look to the right, for example, you can see that mercury has blue light, helium has violet light, and hydrogen emits a reddish light. And the light that is emitted has several distinct component wavelengths. So while the light you see is only actually like one wavelength, you can actually separate out each component wavelength using a prism. And this results in an emission spectrum, which is always the same for each element. So you can see that this emission spectrum will always be attributed to helium. This one will always be attributed to barium. And this emission spectrum can actually be used as an identifier for the element, since it's always the same for each element. And if you look on the right, you can also see that there are differences between the white light spectrum and the emission spectrum, as the white light is one continuous spectrum, there's not individual lines, whereas the emission spectrum does have individual lines and is not continuous. And so the next thing we'll focus on is the Bohr model. The Bohr model is a model in which electrons travel around the nucleus in circular orbits, similar to how a solar system works. So for example, you can say that the nucleus will be the star, and each energy level for the electron orbit, will be a planetary orbit. And each orbit only exists at specific fixed distances, similar to how a planetary orbit works. And the energy of each orbit is quantized, as you can see, 5, 4, 3, 2, 1. And these are stationary states which obey the laws of classical mechanics. And we now know that these stationary states were manifestations of electron wave nature. So no radiation is actually emitted by the electrons while they're in the stationary state, but rather they're emitted during transition. So for example, 5 to 2 will be blue-violet, 4 to 2 will be blue-green, and 3 to 2 will be red. And these transitions between stationary states are not like any other transitions, as you can actually never see the electron between states. They're always in one state or another. And that's the thing that makes them different. You cannot actually see within transition. You can only see the before transition and after transition. And the discrete lines produced on the emission spectra are due to the stationary states only existing at specific fixed energies. So you can see that as we went over before, they're quantized into like terms of integers. And the energy of photon emitted is due to the energy difference between stationary states, and stationary states that are closer together will produce lower energy light. So as you can see, 5 to 2, which is a pretty far transition, it's a large transition, will produce a high energy, low wavelength blue-violet light, whereas 3 to 2, which is pretty small of a transition, will only produce low energy, long wavelength red light. So the problem with the Bohr model is that it still left many unanswered questions, but it was in fact useful for modeling this stuff. And as we stated before, each spectra is a identifier or barcode for each element, as each spectrum is unique to a certain element. And the presence of the atomic spectrum is the basis for flame tests, which are used to identify elements in compounds. So for example, you can see that, for example, like sodium, it has two closely spaced bright yellow lines and will make a bright yellow flame. So if you see a bright yellow flame emitted from an element, you can assume it's sodium due to this fact. And this is also the basis for fireworks having different colors. And while emission of light from elements is actually easier to detect, absorption of light by elements is actually more common for identification purposes. And this is called an absorption spectrum, which is dark lines on a bright background. So you pass white light through a sample and observe the wavelengths which are missing due to absorption. You can see there's dark lines here, bright background, these are the missing wavelengths. And these absorption lines are in the same place as emission lines because processes are mirror images. As you can see, this is bright lines on a bright background, and this is dark lines on a bright background. And while emission spectra will move an electron from high to low, absorption spectrum move an electron from low to high, since it's absorbing energy rather than emitting energy in emission spectra. And this is measured using absorption spectrometer, which will plot intensity as a function of wavelength. And the next topic we'll talk about is the wave nature of matter, which includes the de Broglie wavelength, the uncertainty principle, and indeterminacy. And so we'll go over one thing, which is an interference pattern, which is the assortment of dark and white lines, which we went over in the last section, which happens when you shoot light at two slits, which is like the double slit experiment. And this is the same thing that occurs when an electron beam is aimed at two closely spaced slits. The pattern is very similar. And these are caused by single electrons interfering with themselves, not pairs of electrons, whereas light was caused by two different wavelengths of light. And this is done by recording positions of thousands of electrons over a period of time using a detector, and this causes the interference pattern to be found. So the wave nature of electrons is an inherent property of an individual electrons, which explains the existence of stationary states and also explains why electrons don't crash in a nucleus. As you can see, this is very different from like the expected behavior for particles, as a particle will only have two bright lines, whereas an interference pattern has many bright lines, many dark lines. And this is resulting in the de Broglie relations, which is the formula for de Broglie wavelengths. So it's lambda is equal to h over mv, where lambda is the wavelength of the mass, or rather the wavelength that the mass emits. M is the mass, v is the velocity, h is Planck's constant, and the velocity of a moving electron is related to its wavelength. So essentially what this means is knowing that what the velocity is will mean that you know what electron wavelength is, and if you know what electron wavelength is, you'll know what the velocity is. So keep in mind that if you want to calculate this for electron, the mass of an electron is 9.11 times 10 to the negative 31 kilograms. And now we'll have an example for you to do, which is calculate the wavelength of an electron traveling with a speed of 2.65 times 10 to the 6th meters per second. I'll give you a moment to figure that out. Feel free to pause. Okay, so essentially what you're given already is the speed, which is v. And you know the equation, lambda is equal to h over mv. It is already arranged correctly because you want to figure out the wavelength. And so essentially what you do, you plug in Planck's constant, you plug in the mass of an electron, which is 9.11 times 10 to the negative 31 kilograms. You plug in the speed. And since joules are equal to kilograms times meters squared divided by seconds squared, you can substitute that in for the units. And that will allow for you to cancel units and get that lambda is equal to 2.744651 times 10 to the negative 10th meters. And the reason for plugging in the units is to make sure that the units in the answer are correct, so you can cancel all the units when you're calculating. And it just makes it easier. I mean, if you want to do joules and you know for a fact it's going to, like, you can memorize it's going to end up in meters, feel free to do that. But if you want to make sure that you are correct and like be a little more careful, just substitute in these units for joules. And the uncertainty principle is explained by the electron slit experiment. So recall the electron slit experiment where you emit electron beam through two slits, and you have an interference pattern. So the problem is that any experiment designed to observe electron traveling through slit results in detection of electron particles rather than an interference pattern. And so this means that an electron actually has two states, a particle and a wave state, since if you put a laser in front, you can only see the particle behavior, which is two bright lines, rather than the interference pattern. So this means that however we observe it, however we choose to observe it, whether we want to observe it traveling through the slit or just observe the pattern produced, it forces it into one state. And the diffraction experiment used to observe which slit the electron travels through this is the diffraction experiment. And so essentially what happens is an electron crossing the beam produces a flash, which tells you which slit it's crossing through. But you can never see the interference pattern if you want to know what hole it's passing through, as the interference pattern is only present when the laser is missing. And with the laser, electrons only hit positions behind the slits as a particle. And if you can go back to it, you can see it's similar to this pattern, not at all similar to this pattern. When you put the laser in front of it, it turns into this. And this demonstrates that the wave nature and particle nature cannot be observed at the same time. And this means there are complementary properties. So what this essentially means, complementary properties, is that the more we know of one property, the less we know of another. So essentially, observation affects the outcome. So however we observe it will affect the outcome of what we observe. And de Broglie said that velocity is related to wave nature, and position of a particle is related to particle nature, so therefore you cannot know velocity and position at the same time with infinite precision. And this is related to Heisenberg's uncertainty principle, which is delta x times mass m delta v is greater than or equal to h over 4 pi, where delta x is uncertainty in position, delta v is uncertainty in velocity, m is mass, h is Planck's constant. And this essentially says that the more accurately you know the position, the smaller the delta x goes, the less accurate you know the velocity, which makes delta v larger. Since delta x times m delta v must be greater than h over 4 pi, which is actually a constant. So this is like an inversely proportional relationship. And you can clearly see that the more accurately you know position, the less accurately you will know velocity. And Heisenberg's uncertainty principle solved the paradox of saying an object is both a particle and a wave, since it only allows for you to introduce one at a time. You cannot introduce both at the same time. And so this results in indeterminacy and probability distribution maps. So whereas particles will move in a trajectory according to classic physics, such as a baseball, where after being hit you can predict exactly where it's going to go. Since position and velocity are needed to predict this trajectory, you can see it's going to probably go this way. It's the forces on the gravity, the position of the ball, the velocity of the ball. It's going to end up right here. And so this means that Newton's laws, which are like classical physics, are deterministic, as the future is going to be determined by the present. So since these properties are present, you know exactly where it's going to be in the future. And two balls, which are hit in the same place with the exact same velocity, will land in the same spot. However, this is not true for electrons, as both position and velocity of electron cannot be known. So therefore, the trajectory cannot be known. And this is replaced with the probability distribution map, which tells you it's like a probability of where the electron will be. Whereas a ball, you know exactly where it's going to be. And this concept of probability distribution map can be compared with baseball, as the catcher can predict when a baseball thrown by pitcher will cross home plate. And however, the same position is impossible for an electron, as you cannot exactly predict where the electron will go, since you cannot know the trajectory of an electron, as the electron would go in a different spot every time, which is indeterminacy. So the future path of the electron can only be described statistically. So for example, you can talk about like comparing it to the quantum mechanical strike zone here, which is going to predict exactly where, like, it's not really predicting exactly where, it's just going to predict like a probability of where the electron, where the ball will go after being thrown. And this is similar to recording many electron throws, which will allow for a statistical pattern of where electron crosses the plate to be produced. So let's just say each ball is an electron, and the pitcher is throwing an electron. And you can predict, like, you can see 20%, 40%, 70%. You have a statistical, you have the ability to perform in a statistical model and create this to make it reproducible. The pattern will be reproducible for the statistics. And this is essentially a map which shows the probability of the electron crossing a certain area. And for like an atom, this is an orbital, which are probability distribution maps for electron within atoms.